Welcome to Train Signal. You're watching a lesson on TCP/IP communication. Now, I'm really excited about this lesson. And the reason why is because up to this point, I've used this term TCP/IP quite a bit. But I couldn't really go in and explain all the ins and outs behind it. Well, guess what? Now I get to go over those with you so that you can fully understand how TCP/IP works. So the first thing I want to tell you about TCP/IP is, well, let's make sure you know what the letters stand for. Okay, TCP is the Transmission Control Protocol / IP, which is the Internet Protocol. You really need to know this? No, but it never hurts to understand what the acronym stands for. The one main thing I do want you to understand about TCP/IP, and this is the first thing that we're going to get into here, is you may remember from a previous lesson that I mentioned that a protocol is a set of rules and procedures for communication. Well, let's break that down further and remember that some of these higher level protocols, like TCP/IP, are actually a set of individual smaller protocols. Okay, so we could say an individual set of rules and procedures that are all stacked together. You put them all together and you end up with a protocol stack or sometimes a protocol suite. They're the same thing. Okay, I mean, I've heard of the term protocol stack, protocol suite. They're synonymous. They can be interchanged with one another. So the first thing we're going to go through is the actual architecture of TCP/IP and see how that suite of protocols is made up. So the first thing when it comes to that architecture is that it is based off of the 4-layer DARPA model. Okay, DARPA is D-A-R-P-A. And I really want to emphasize this is a 4-layer model because in a previous lesson we learned about the OSI model, which is a 7. I can't do that on one hand. It's a 7-layer model. Each of the 4 layers in this DARPA model have individual protocols. We're going to go over many of them, which will work together to form this suite or stack that we call TCP/IP. So this is what the 4-layer DARPA model looks like. You'll see here that the top layer, just like with the OSI model, is the application layer. We, below that, have a transport layer. Then we have an internet layer. And finally, at the bottom, we have the network access layer. Now, just like the OSI model, where you needed to know what the names of the layers were and the order of those layers and what basically takes place at each layer, pretty much the same holds true for this model as well. And as a matter of fact, you'll see here that the TCP/IP model, which, that's pretty much interchangeable. Some will tell you that that's not technically accurate to interchange TCP/IP with DARPA. There are some technicalities to it, but for simplicity and understanding, from here on out, we'll just call it the TCP/IP model. You'll see that that model somewhat maps to the 7-layer OSI model. And I will tell you again, this is just rough. Okay, this is just a rough mapping. The top layer of the TCP/IP model, although it shares the same name, which is application, as the top layer of the OSI model, you'll see that it roughly maps to the top 3 layers of the OSI model. Now, why is this important? This has to do with functionality. Okay, when we learned the OSI model and we saw the different functionality in each of the layers, well, it's that similar functionality taking place at certain layers in the TCP/IP model. Now, the transport layer, you'll notice, is almost a perfect match with the transport layer from the OSI model. The internet layer is almost a perfect match with the network layer of the OSI model. And the network access layer roughly maps to the bottom 2 layers of the OSI model. All right, so that's just kind of basically looking at the layers from a perspective relative to the OSI model. Another thing that you should take into consideration is that the functionality of the TCP/IP model is exactly the same as the functionality of the OSI model. If you watched my OSI model lesson, I had an actual animation here where I showed how the sending computer starts with raw data. That data is then sent down through the OSI model with each layer adding header and then some trailer information on the way down. It goes across the network cable once you get down to the network access layer. And then on the receiving side, the network access layer takes it off the cable, sends it up through the OSI model, with each layer stripping off the information that the corresponding layer from the sending computer had added, until eventually up at the top at the receiving computer, you end up with raw data. If this does not make sense to you, and if I went through this too quickly, make sure you go watch the OSI model lesson where I explain this in more detail. Now, the next thing that you need to know when it comes to this TCP/IP model is you need to understand some of the different protocols that are involved with the protocol stack. Okay, if we're going to talk about protocol stack or a protocol suite, you have to know what some of those are. Now, up at the top in the application layer, I have 6 of them listed for you, but I will tell you that that is not an all-encompassing list. Okay, in other words, there are many more protocols that exist up at the application layer. And you'll notice that many of these protocols relate specifically to some application or service that we find in the operating system. If you look down at the bottom in the network access layer, I have Ethernet and token ring listed, and realistically, Ethernet is the only thing that is used right now. And as I've mentioned in previous lessons, token ring can be used as an access method, but primarily only with certain fiber-based, ring-based WAN technologies. In a local area network, we're talking almost strictly Ethernet. Now, we're not going to put a whole lot of focus on those top layer protocols or the bottom layer protocols. What we do have to do is we have to look at all 6 of the middle layer protocols. Okay, we have to take a look at TCP and UDP, which are the 2 transport layer protocols. And we have to understand IP, ARP, ICMP, and IGMP, which are the internet layer protocols. So starting off with the transport layer protocols. The first one that we're going to look at is something called TCP, which you'll notice is obviously important because it's part of the name TCP/IP, right? So TCP, which is Transmission Control Protocol, is used when you have a one-to-one connection, or what we'll see in a little bit is called a unicast, where you have one computer sending specifically to another computer. That's where we would use TCP. It is what's known as a connection-oriented protocol, and we need to talk about that a little bit as far as what we mean by connection-oriented. But before I get to that, I also want to just state that TCP is considered to be reliable communication. Now, here's the reason why it's connection-oriented and it's reliable. As far as it being connection-oriented, this means that a connection must be established before data can be exchanged. Okay, so in other words, if I have some data that I need to send to you, I can't just send it. I have to first get your attention and make sure that we are ready to communicate and that we have a connection to have that communication before sending the data. The way TCP does this is through the use of a 3-way handshake. So let's talk about how this 3-way handshake works. Step 1, the computer that has data to send will reach out to the other computer and say, hey, I'd like to talk to you. And here's some information that you're going to need if you're going to communicate with me. Okay, so it's just reaching out saying, hey, I got something to tell you. I got some data for you. Here is the information that you would need to know in order to communicate back with me. Step 2 of the 3-way handshake is the receiving computer will say, hey, thanks. I got your information, and here's the information you would need to be able to communicate successfully and clearly with me. And then the third part of the 3-way handshake is the original computer saying, okay, great, I got your information. And it's kind of one of those where it's like, okay, so you obviously have my information, I have your information, we're in sync with one another, let's begin talking. That is basically how the 3-way handshake works. Now, the part where we talk about reliable communication, it goes beyond just the 3-way handshake. Okay, that just gets us connected. The other thing that makes TCP so reliable is that for every transmission, every time I send you some information, you reply back with a confirmation, letting me know that you got it. Okay, so I kind of think of it as like sending a letter certified mail. If I send you a letter certified mail, I don't just put it in the mailbox and hope that you get it. No, I send it off, and then you have to sign for it, and then I get sent back to me that little receipt with your signature on it that says, yep, it's been delivered. And that's how TCP works. I send you a packet of information. You have to reply back to me that you got it. If I don't get that reply back saying that you got it, well, then I'm going to send it to you again. I'm going to assume it got lost in transmission, and I'm going to send it again. Now, the other transport layer protocol is UDP, which stands for User Datagram Protocol. This is what is known as connectionless. Okay, so there is no connection established. It is typically used in some form of multicast or even a broadcast, and we'll learn about what those are in just a few minutes, but it's where one sender is sending it out to many recipients. So to go out there and establish all these connections with many other recipients just doesn't make sense. And it's also considered to be unreliable communications. Okay, the way it works is, I like to think of it as, now let's just say you were sending a letter and it was not certified mail, right? You just put it in the mailbox and you hope it gets there. That is pretty much how UDP works. The sender has some data to send and it just gets sent and hopefully you get it. And the best way to think of this would be the multicast scenario. And I know I'm getting a little ahead of myself here, but in a multicast, the example I could give would be, let's say you're watching some streaming video on the internet. Well, the website which is putting that video out there, well, they don't know who the recipients are, right? They just put it out there, and then anybody who subscribes to it can receive that information. Well, all the packets of information that I'm streaming out there that make up this video that you're watching, you may not get every one of them. As a matter of fact, you may have had an experience where you were watching some streaming video, and then it just kind of froze up. And it froze up for, let's say, 2 seconds. And then it released, and you continued watching whatever you were watching. That's what we're talking about when we say unreliable communications. The reality is most of that data is still going to get there. But if it doesn't, it doesn't. You just move on. So those are your transport layer protocols. Now, the internet layer protocols. The first one, well, again, the first one of transport layer was TCP, which of course is part of TCP/IP. And what's the other half? IP, the Internet Protocol. And as I've mentioned many times, TCP/IP is needed for the Internet. The Internet Protocol is responsible for addressing and routing. You remember when I said that the Internet layer of the TCP/IP model maps to the network layer of the OSI model? And you remember that the network layer of the OSI model from a different lesson we said was responsible for addressing and routing? This is actually why we say that. Because we know that in the OSI model, the number one protocol that's actually being used is TCP/IP, and this is where that mapping is. So IP is responsible for things like dealing with IP addresses, and then being able to route and determine how we're going to get from point A to, let's say, point Z, right? We may have to go through all sorts of different routers to get from one network to another. The next internet layer protocol is ARP, the Address Resolution Protocol. This is responsible for resolving an IP address to a physical hardware address or a MAC address. And I will tell you, if that confuses you, some people look at it the other way around. And I've always taken a stand of, you could say it either way. You could say it's resolving the hardware address to an IP address. Okay, the idea is, we'll just say it's resolving between the two. Okay, in other words, we have an IP address which is used to determine the actual routing as far as how you're going to get from point A to point Z. But once we get to the actual network where the recipient exists, we need to resolve down to a physical hardware address, the actual hardware address of the network card, to then be able to deliver it to that network card to get it into that computer. Okay, so ARP is a protocol that does that resolution. I will also tell you, even though we're not going to go into it at this point, ARP is also a utility. There's actually a command line utility, which is also ARP. And it is a utility which is related to resolving IP addresses and MAC addresses. But just in case you've heard these little tidbits of information, I want to make sure it's not confusing to you. It's a protocol and a utility. The next protocol is ICMP, which stands for Internet Control Message Protocol. This is a protocol which is responsible for diagnostic and error reporting. This is a protocol that is used to attempt to make TCP/IP more reliable. Still doesn't make it perfect. There will be dropped packets, there will be mistakes, and especially if you're using UDP transmission, there will be dropped packets that just never get there. But what ICMP does is if there is some form of error in transmission, it will attempt to send back an error message. The way I like to think of this, using the mail analogy that I keep going back to, is if you were to send a letter, and when you send that letter off, the post office realizes that you sent it to an address that doesn't exist, or maybe the person doesn't exist at that address anymore, right? Maybe they deliver it, but then the person in that house says, yeah, they're not there anymore. They then attempt, and they being the post office, they attempt to send that letter back to you, the sender. And they put a stamp on there, like return to sender or something like that. They attempt to send it back to you, but there's no guarantee that that's going to ever even make it back to you either. And that's exactly how ICMP works. The last of these internet layer protocols is IGMP, which stands for Internet Group Management Protocol. And I'm kind of laughing here because I will tell you that the one main thing that I'm going to tell you that you should know about IGMP is that it's not ICMP. And the reason I say that, above and beyond anything else, is because, well, look at it. I mean, I, M, and P are all the same, and the letter G almost looks like the letter C, but with an extra little thing on it. So you don't want to confuse the two. And then on top of that, there's not a whole lot that you need to know or worry about when it comes to IGMP. It has to do with managing multicast group membership. So I mentioned multicast a few moments ago when we were talking about UDP. We talk about where you have like streaming video or streaming audio, and only certain people will subscribe to receive it, right? It's been broadcast out on the internet. It doesn't just automatically show up on everyone's computer. It shows up on the people who have requested to receive it. And they get that by getting a multicast IP address, which IGMP will then manage. You shouldn't need to know much more than that about IGMP. So those are the 4 internet layer protocols. So as a whole, I will tell you that that is pretty much everything that you need to know about the TCP/IP architecture and the actual model and how it all functions together. And it's not a lot, but it's extremely important. The next thing that I want to talk to you about is different types of communication. And I've already mentioned some of these types of communication while explaining, well, the architecture. Okay, the 3 types of communication that I want to talk to you about, first of all, are unicasts. And a unicast is a one-to-one communication, meaning one computer has something to send to another computer. It's a very direct communication. A multicast is considered one-to-many, but as I've already described, not everybody, just a lot of people, anybody who wants to subscribe to it. And a broadcast is where you have from one to all, or everybody, or at least everybody within what's called a broadcast domain. And that, by the way, is determined based upon the equipment that you have in place. Everybody who's on the same side of a router is in the same broadcast domain. And if there's a broadcast, which means you send it to the network address that has the network ID that you're on with all ones, or what usually equates to all 255s for the host ID, which tells every computer, this is for you and you must receive it. So that's a broadcast. Now just to illustrate this, this is what it looks like. A unicast has from one computer directly to another computer. Multicast is one to many, but you'll notice from this picture, not all. And then the broadcast is from one to all of the computers on that same network. So those are the 3 main ways, and really, for the most part, the three only ways that communication takes place in TCP/IP. And I will tell you that this is very specific to IP version 4. You'll see there are some ever so slight variations to this when using IP version 6. Now, the last thing that I want to talk to you about here in this lesson is something called access methods. Or in other words, the method in which data can access the network. There's 3 access methods I want to go over with you. The first being something called CSMA/CD, which stands for Carrier Sense Multiple Access with Collision Detection. Now, before I go any further, even though I said there were 3 access methods, I want to tell you this is the one that I want you to absolutely understand. Okay? And the reason why is because this access method is also known as the access method for Ethernet networks. The #1 most heavily used type of network out there. Okay, so you have to understand how CSMA/CD works. Now, the first thing I want to do is break down those words, carrier sense, multiple access with collision detection. Carrier sense means that the computers can sense if there's already data out on the cable. Okay, so just hold on to that for a moment. I'll explain why that's important. But the next words are multiple access. That means all computers have access at the same time. There's no like predefined line, like everyone get in line and then you can take your turn. We'll see how that comes into play with a different access method. The last words are collision detection. Although you're going to see that there's a process here that which kind of helps avoid collisions, or we hope we can avoid some collisions. Collisions do happen, and what I mean by collisions is 2 computers both putting data out at the same time, the data comes together and collides. When that happens, we can detect that, address it, and then figure out how to solve that situation. So what I want to do is give you kind of a real-world analogy to how this all works with CSMA/CD. What I like to think of it as is I like to think of it as a polite conversation. And that polite conversation can be with 2 people. So you and I can be having a conversation, or there could be a room full of people. It works the same way. If you are a polite person, what is the first thing, the very first thing that you do when you have something to say? That's right, you listen, right? I intentionally gave you some silence there. Before you speak, you wait, you listen and say, okay, I don't hear anybody else talking, I'm going to talk, right? Because it's rude if you talk over somebody else. And I'll tell you what, if you were in a classroom with me right now, I would have talked over you all the time. Why? Because I'm an instructor, and so I think I get to be arrogant and rude. So we're not talking about that. We're talking about a polite conversation. And that is the carrier sense aspect of this, right? I get to listen. And when I hear that silence, or when the computers don't see data traveling, they can go ahead and transmit. And again, it is multiple access, so everybody's doing that at the same time. Meaning if you and I were talking to each other, there's no rules that say, I get to talk, you get to talk, I get to talk, you get to talk. No, it doesn't work that way. Either one of us can talk whenever we want. So again, if we think about it, it's a polite conversation, we listen, nobody's talking, we go ahead and say something. But even in a polite conversation, what happens every once in a while? What if you and I both had something to say, right? Our brain said, oh, I want to tell the other person something. And there was silence, right? We're both listening. No one say anything. We might both speak at the same time. And what happens? If you think about it, what really happens? If we both speak at the same time, our voices collide. Neither one of us really understand what the other one was saying. We don't really hear it clearly. And so we stop talking. And that's what happens when 2 computers both talk. You get that collision. The data doesn't go any further. It dies right there on that collision. Just like if you and I were talking, we both stop talking. And what happens at that point is there is a random amount of time, and it's truly random, meaning the computers will each wait a random amount of time, hopefully not the identical random amount of time, before they attempt to transmit again. And that's kind of like what would happen if you and I were speaking. If we both spoke at the same time, our voices collide with one another. We stop, right? All right, sorry, other one's talking. And some way, maybe there's some little body action or, you go first. But one way or another, there's a random amount of time, and then eventually one of us speaks first and then the other. That's exactly how Ethernet networks work with CSMA-CD, where they listen to see if no one else is transmitting. If they're not, they transmit. If they go ahead and transmit accidentally at the same time, there's a collision, that data stops, and then they wait a random amount of time and try again. All right, so again, I want to emphasize that's the access method I want to make sure that you are clear on. You have to be clear on this access method. Now, the second access method I want to talk to you about is very, very similar. Okay, it is CSMA/CA, which again stands for Carrier Sense Multiple Access. That's the same, and the meaning is the same. But now the CA stands for collision avoidance. Now, you remember how I said, CSMA-CD, we're already trying to avoid collisions, but we do it just by listening for silence, right? Well, with CSMA-CA, where the CA stands for collision avoidance, there's a more direct way of, actually giving that avoidance. Not only do we listen to see if no one else is speaking, but when that moment happens, okay, so if I'm a computer and I go, nothing else on the cable, I don't just transmit data. I don't just start talking. What I transmit is a very, very, very small little packet that basically says, hey, everybody, I'm about to say something. The analogy I like to use here is it's almost kind of like, picture if we were in a room, or again, not just necessarily a room full of people, but let's say it was just me and you. And instead of just listening to see if the other person was talking and waiting for the silence, let's say if before we spoke, we actually raised our hand. Right? We actually raise our hand to let you know, I have something to say. Picture it like if you were in a room having a meeting with a group of people. People raise their hand. Raising of the hand tells everyone else, hey, I'm about to say something. So you all shut up now. That's how CSMA-CA works. Now, I will tell you, even with collision avoidance, you can still have collisions. But the collision doesn't take place with the data, so it's not the actual data that collides. Two people can raise their hand at the same time. Okay, so two computers can send out that little piece of information. And if that happens, if that little packet that says, hey, I'm about to transmit, if those collide, well, then you revert back to CSMA-CD in the sense that there's a randomness before one of those computers transmits that little packet again saying, hey, I'm about to send some data. And I will tell you that CSMA-CA, although it still may be used, and I'm not overly familiar with this to know how much it's used in this arena, because I'm more of a PC guy and a Windows guy. But I know on the Apple side of things, the old Apple Talk networks used to use CSMA-CA. But in today's world, where you see this most often is in wireless networking. Okay, when it's going through the air, we use CSMA-CA. Now, there's a third access method, which we really don't see very much anymore, or at least not in our local area networks. We still use this in some of our WAN technologies, but it's something called token passing. And this is, well, what would typically be used in a token ring network. I mean, that's, again, there are WAN technologies. I could get real literal with you and talk about sonnet rings and all this. The token ring network, which is really kind of a thing of the past, that's where token passing is used. And the idea behind it is what's called a deterministic access method, meaning we don't have multiple access anymore. Everybody doesn't get to be out there at the same time. Everyone has to take their turn. And I'm not going to go into great detail about how this whole process works, but the idea is if you picture a bunch of computers in a ring, okay? If you remember from the the different topologies that I went over with you in a previous lesson. There is the ring topology. If you picture computers set up in a ring fashion, each one of those computers gets to take their turn in the ring. And what they do is they pass this token around. And the token goes around for no other reason other than to let a computer know, hey, if I've got the token, I can send data. And when I send that data, the data must go all the way around the ring, get back to me, at which point I release out a free token so the next guy has a chance. Okay, so again, I don't want you to get too focused on it. I just want you to understand the basic idea of it being this deterministic access method. So those are the three access methods, but remember, the main one to understand is that CSMACD. And I'll tell you what, that also brings us to the end of this lesson. And you know, I told you at the beginning of this lesson, this was a very exciting lesson for me. And the reason why is because TCP/IP is everything, right? I mean, it's all about internet communication, which is everywhere. Okay, you have to have TCP/IP for that. You'll hear the term TCP/IP come up in probably just about every single lesson in this course. So this was my opportunity to make sure that you are solid on how TCP/IP communication works. And I hope I've done my job, and I hope you've been able to grasp everything that you need to get to understand exactly what it is, because you're going to hear that term a whole lot. So with that said, that's all I have for you, and so I'll see you in the next lesson where you're going to understand TCP/IP.